You're listening to a Raconteur Studios podcast.
Do you know how to keep your skin cells looking younger for longer? Well, there's a very interesting concept now, and it's all related to the tiny little mitochondria that are within our cells.
And if you don't know what a mitochondria is, then don't worry, because we're here to tell you everything you need to know about this little powerhouse structure within our cells.
Because that is the thing really that's going to be able to protect those skin cells and improve skin health and longevity. Hello and welcome to the After Hours Skin Clinic, the place where the skincare conversation never stops.
We're consultant dermatologists Dr. Ellie Rashid
and Dr. Emma Craythorne.
And in this episode, we're walking you through the groundbreaking science behind one of the newest developments in skincare science.
Okay, so picture this. Within our skin cells, we have these tiny little organelles called mitochondria. And the mitochondria essentially are like the power plants. You know, they provide all of the energy to make sure that our skin cell is working properly. And this power plant, this energy source, the better it's working, then the more efficient that cell is.
So I always think of it as like the mitochondria is the little battery within our cell.
It even looks like a battery.
I genuinely think that as well. It looks like a little battery with little squiggles inside. So it's like a little battery within our cell. And if that battery is optimum and working as best it possibly can, then it means that that cell will function in a better, healthier way. And I guess the main reason why we look at mitochondrial DNA, so the mitochondria has its own little genetic DNA.
It's like a cell within a cell.
A cell within a cell with its own little DNA, like in a little ball. And the reason why it's important to look at mitochondrial DNA as some sort of marker, like a surrogate marker for cell function, is because when you get things like oxidative stress or external factors like pollution, UV damage, etc., it all can affect the mitochondrial DNA and it doesn't have the capacity to repair itself.
So if you imagine within that little mitochondria, you've got the DNA, and the DNA is telling that little battery how to work. But things damage that DNA. And unfortunately, in the mitochondria, it can't repair itself in the same way that it can within the main body of the cell. And therefore, the mitochondria's DNA starts to decline. And what's quite interesting is that you can measure that rate of decline. So when that battery is working super optimally and everything is very efficient, it's say putting out 100%, but over time it starts to drop quite naturally because all of these things attack it over time until it reaches a point where it just doesn't work anymore and it can't kind of power the cell. What's interesting about the mitochondrial DNA is you can measure this. And so you can measure it to see how effective it's being. And you can also then measure it if you put things in place to try and protect it, to see if that thing has protected it.
Yeah, and you can look at the rate of decline of the mitochondrial DNA. So if you put something in place to protect it, does it mean that it's slowing down that rate of decline versus mitochondrial DNA that's not been exposed to whatever that thing is that you're trying to assess?
Exactly. And usually these things that we know that attack the mitochondria really are the things that really attack the rest of our skin. So things like ultraviolet radiation. So you have all of these different things that target and damage the mitochondrial DNA. And the vast majority of it relates to oxidative stress. And so ultraviolet is going to damage it. Ultraviolet A and ultraviolet B is going to damage it. You're going to get damage from pollution. You're going to get damage from kind of even being unwell, poor diets, low intake of good foods. All of these things will have an impact on how that mitochondria is functioning. And what I always find really interesting is that as it starts to decline, it becomes a less efficient battery. And as a less efficient battery, it actually then its rate of decline starts to increase. It becomes more damaging to itself.
Do you remember when the batteries used to have this little thing that you'd put on the top and tail of a battery and it would tell you how much energy was left within that battery?
You can still see that on the side of some of them.
Yeah. I always think like the tests that look at mitochondrial DNA, similar to that, like how well is it functioning? How much energy has this battery, this little power plant within the cell, how much has it actually got? And then that's a really good marker to see how much damage it's been exposed to.
And it's also quite interesting, isn't it? Because it doesn't go back up. Once the damage happens, it's there and it's fixed and it stays. It's not like you can go from 100% down to 60% and then back up to 80%. Once it's down, it's down.
Which is why we need to care about protecting it early on so that our skin cells can function in the best way possible for as long as possible, because we just don't want to damage it. We also have some exciting news to share. One of the reasons we're tackling this subject is because we've both had a pretty exciting month, and it's got a little something to do with mitochondrial DNA. Emma, do you want to explain all?
Well, it has been a really exciting month because it has been the launch of our day product from Clara called the Day Script. And one of the exciting things about now, the more we're understanding about mitochondrial DNA, is that there's now new tests that have been developed to measure the mitochondrial DNA that are very, very quick. And all they also require is a simple swab of the skin. And whereas before you might have given somebody a cream and you wouldn't see those clinical changes for maybe 4, 5, 6 years to know that that cream is having a benefit, you're now able to see that this cream is having a benefit within about 3 months. Because instead of measuring the long-term changes, which are things like wrinkles or brown spots or inflammation, you're instead measuring the precursors to all of those things, which is the mitochondrial DNA. The mitochondrial DNA, the more it can be preserved, means that the cells are functioning better, and ultimately cells that function better will behave better and ultimately then look better. Now, we know that putting on an SPF every single day will make your skin cells behave in a younger way. And that's because you're not getting the same amount of ultraviolet damage to the skin. So the skin cells behave and stay younger. That is a fact. Those big studies that bore that out took 4 or 5 years until they were able to then make that claim that you get better skin from wearing your SPF. But also, we've got lots of claims from multiple other sources within skincare of things like putting peptides on our skin, putting antioxidants on our skin, the importance of the skin barrier, the skin microbiome. And so I wanted to integrate all of the best of the evidence that there is out there from all of these different fields and put that in alongside these very good filters that we have for the SPF. And so I didn't really want to then run a study that was going to take 4 years to be able to say, okay, yeah, this cream is better than just putting on your SPF. And that's why it's wonderful that there are now these new ways of investigating and primarily looking at how that mitochondrial DNA is protected. You know, you see these changes quickly. But anyway, enough about the Day Script.
So I guess whether you're a Clara user or not, this is skincare science that everyone just needs to know about.
And what better place to talk about it than here on the After Hours Skin Clinic?
Recently, Emma spoke to leading skin scientist and expert in mitochondrial DNA, Professor Mark Birch-Machin. He's got decades of research experience behind him, and Mark has helped to uncover how everyday factors like sun exposure, pollution, and stress can affect our skin at a cellular level.
I mean, I don't think there's anybody better placed to talk to us about mitochondrial DNA and mitochondria. I mean, he has geeked out about this his entire life. He knows everything there is to know about the mitochondria.
So let's hear what Mark has to say about the role of mitochondrial DNA in the aging process.
It does get a bit technical, just so you know, so you have to stay on your guard.
Mitochondria are actually pivotal in the aging process. And from a mitochondria point of view, kind of a couple of things happen as we age. The ability to make energy declines in mitochondria, so they get worn out, and something needs to be done about it. And the second thing that happens is the fact that mitochondria produce 90% of cellular stress through a cascade mechanism. So they're the start of it, and it's like knocking over a domino. You knock over one domino and then the whole cascade happens through the rest of the cell. And so it's akin to the exhaust fumes from the power station. You know, these oxidative stress molecules are like the harmful exhaust fumes. And so what happens is we get older, those exhaust fumes get more. All right. So you've got two things going on. You know, your batteries are wearing down and you've got more exhaust fumes kicking around your body, and you need to do something about that as well.
So if we think about the mitochondria and its production of energy, we know certain things age our skin faster if we're in ultraviolet radiation, but What is it about mitochondria that makes it age more quickly?
Yes. So if you imagine a kind of a triangle of damage, the three components of that triangle are the mitochondria themselves, how they work, the function of them. And the second component is these exhaust fumes, the oxidative stress, or we call them reactive oxygen species. And the third component is the DNA housed inside the mitochondria. And actually the DNA housed inside the mitochondria is unprotected. It's naked. It isn't protected by lots of proteins and things like that. And also the mechanisms generally used to repair DNA damage don't exist in mitochondria. Some do, but actually, for example, the repair mechanism for sun-induced DNA damage doesn't exist. So essentially what you can see is mitochondria, they can't repair their DNA damage. But unlike nuclear DNA, there's lots of copies of DNA molecules within mitochondria. Why is that important? It's important because the molecules that are not damaged can help out the ones that are damaged through a process called complementation. It's like the good ones help the bad ones. You know, it's a nice view of society. If you've got, if you're okay, you help out those that are not okay. And so what that does is it enables the cell to continue living, even though there's a lot of damage there. And so the mitochondria can still work because they pass along their resources along the mitochondria.
These mitochondrial DNA, do they get that direct DNA damage from ultraviolet B radiation?
Yes, they do. So what happens is the fact that through UV and pollution, and actually we've shown, particularly in skin, through stress, sleep patterns, things like that, that stressed skin will actually result in stressed out mitochondria because of the fact that they're easily damaged, they can't repair themselves, and actually damage will accumulate in those cells because actually the good ones will help out the ones that are damaged. And so what does that mean? That means the fact that actually, because the DNA codes for some of those proteins that help to make the ATP, it means that energy production or bioenergy is compromised. If bioenergy production is compromised, then that leads to more exhaust fumes from your power station. And more exhaust fumes from your power station will actually cause oxidative stress, and a stressed cell will actually damage more mitochondrial DNA or damage nuclear DNA as well. And so obviously then the whole pattern repeats and you get what's called a vicious cycle of aging. And so there's an opportunity there to slow down that vicious cycle of aging in terms of skin health to make our skin look better for longer rather than we look like a 70-year-old when we're 50 or something like that. So that's the challenge, yeah.
Okay, so that's our cells being damaged by oxidative stress. And so what then happens is the mitochondria are just not functioning in quite the way that they were before. They slow down a little bit, but they also make more exhaust fumes that are causing a bit more damage to that cell. In terms of things that people are doing or one could do to try and slow down that process, obviously protection from UVB and UVA is right up there as number one, I'm going to guess.
Yeah.
But what other things have been tried and tested that we know accelerate that damage or can potentially decelerate or protect the mitochondria?
Yes, absolutely. So UV tends to be the major determinant because that's what we started with. And so since then, we've looked at the effects of pollution and published on that. We've looked at particularly particulate matter and diesel, and we actually walked around the whole genome. If you look at mitochondrial DNA as being a circle, so we actually went around the whole circle of DNA and actually treated skin cells with UV and pollution and found out which areas of that genome are more susceptible to UV and which are more susceptible to pollution in terms of damage. And there are certain hotspots within the genome where there's a difference between UV and pollution. And so, yeah, pollution will actually damage the mitochondrial genome. But also we've done studies with shift workers and sleep patterns and stress and lifestyle and things like that. And there are elements of lifestyle which will stress the skin, which is reflected in mitochondrial DNA damage. And some is published and some isn't published. But it just shows the fact that the mitochondria are very sensitive to lifestyle effects. And actually, there'll be other aspects of lifestyle that we've not looked at. So in terms of UV and pollution, UV clearly will damage mitochondrial DNA. Pollution will damage mitochondrial DNA.
And when you talk about pollution, is that pollution that you're inhaling in, or is that pollution that is in direct contact with your skin?
That's an important point. So this work has been done on pollution that would be in contact with skin. So we've done it in skin equivalents, and so very much that rather than inhaled pollution. Really.
So can you actually measure then on your skin how good or bad your mitochondria is? Is that something that can happen?
You can. So, and it's been a long journey. You know, you need to value the journey and celebrate the small wins and all that kind of stuff. So I guess it was a 15-year journey from first looking at mitochondrial DNA damage in biopsies, full thickness biopsies. So we're talking 6 millimeter, full millimeter punch biopsies, which for most people, you wouldn't elect to have one of those. You wouldn't get up in the morning thinking, I'll have a 6 millimeter punch biopsy today.
So for people listening, the kind of gold standard we would think of in dermatology when we want to look at what the cells are doing, look within inside the cells and see the shape and behavior of them is to do something called a punch biopsy. And this is a full thickness sample of tissue that comes out in the form of a circle. It looks like a very tiny little apple core. And you can put this under the surface of the skin and then extract this core of tissue. And that is really what we think of as being the gold standard. But nobody really wants to have 6 millimeters removed from their face because you definitely have a scar. And so you've gone from a 6 millimeter punch biopsy right the way down to inventing essentially a swab that doesn't go into the skin that will give us the same information.
So we ended up using a non-invasive skin swab, which is like a kind of robust cotton swab at the end of a stick, essentially. But you had to do the journey to actually validate the skin swab. You can't just go to a skin swab and expect, oh, this works. Because obviously a skin swab will only pick up the surface skin cells. And so that's why it takes a long time, because you have to cross-validate, you have to make sure it's accurate, you publish in peer-reviewed journals, you allow other people to look at it, criticize it, everything else. And so what we've got it down now to is this non-invasive skin swab where we're able to measure, as it were, the tower of mitochondrial DNA damage. So every time we go out, our skin gets stressed, UV pollution, we get more mitochondrial DNA damage. So it's like an increasing tower of damage, or which is like a diary of damage. And so the challenge is, can we read that diary? Yes, you can. And when we started, we could read it in biopsies, but now we can read it using these non-invasive skin swabs. The DNA doesn't lie. It's damaged or it's not, which is actually very helpful in terms of helping to give a reflection of the skin health, but also how well interventions are working or not working, and how lifestyle changes are working or not.
I mean, it's pretty mind-blowing that all of that research you've done over decades and decades, I mean, walking around a mitochondrial DNA genome in itself is mind-blowing, but all of the other experiments that you've been doing, building up to something where you can now essentially take a swab of someone's skin and that swab will reflect the mitochondrial DNA health of that person from that site. I mean, that's amazing.
It is, because your head is kind of down working hard away at things. You don't often step back and reflect about how amazing it is, because you're thinking, okay, I've done this. What's the confounder here? What's this? What's that? And so you're actually being more critical than anyone else on the planet about your own work, which is a good thing. But sometimes it makes you not as reflective and appreciative of the contribution that you've made. And it's not until you do things like this and actually you hear from a learned colleague who you respect to say, actually, that's amazing. And you think, actually, no, that is. Having reached the age of 142, I'm 63. It makes you even more humble that actually you've got to the stage that you've done through kind of hard work, and thinking, actually, that I'm glad I did that. I'm glad I didn't ignore that. It's like, don't despise the small things, all right? Because they eventually get to be that breakthrough.
I think what the most amazing thing about this is this idea that we always think about what we'll learn in basic science and in the laboratory and how we can translate that so it actually improves patients' lives. And this is just one of many things I know that you've done. But in this particular example, being able to suggest how things might actually truly have an impact in a very easy way, to be able to get lots of numbers for studies so that we can say, yes, this is going to make a difference to your skin health. This is essentially going to make a difference potentially to this word that's used a lot at the moment, longevity, and instead of having to wait for months and months and months and months and months, or years and years and years to see if something you're taking or doing is going to have an impact on your longevity, you can probably do this in a matter of just a few weeks now. Is that right?
That's right, yes. What this technology enables us to do is within a matter of weeks, and you actually have a result in your hand. And actually, it's like anything where if you know that something that you're doing is working, you'll continue with it. And if you're doing something that isn't working, then you can either change your lifestyle or pivot to another type of intervention.
In my own clinical practice, if we take the group of patients who have xeroderma pigmentosum, so this is essentially a condition where following DNA damage to a cell, the person with XP, as we would call it, isn't able to repair that damage. And this is a lifelong condition. It's genetically inherited, and you start to see skin cancers forming, usually at a young age. But for some people, they do have some level of repair. And actually, they may not be getting their skin cancers until they're in their 20s or 30s or 40s, but then they get a lot. A group that's particularly difficult is actually this group of teenagers and young adults, where assessment of risk is slightly different. As a young child, your parent will put your SPF on for you. And as an adult, you've kind of got the wherewithal to assess risk a bit better. But this group is a bit different, and actually often fall a bit behind in terms of wearing their SPF because they're not seeing the immediate benefit of it.
Yeah.
And actually also think, well, 40, that's so old. And I'm never going to get my skin cancers. I mean, at 40, that's ages away. So reminding somebody to put their SPF on doesn't really have the effect. But I think that understanding that the reason why you get skin cancers is from your DNA damage. And I think that if you were then able to say in a very brief form of time, you've only got to wait 12 weeks, 3 weeks, you can see the intervention that putting an SPF has on, rather than waiting for the 10, 15 years whenever the skin cancers start to arrive. This is such an amazing new investigation that we have for situations like this, and for many situations where people don't quite necessarily believe the impact of what something like SPF might have on their skin.
Yes, absolutely. That's a fantastic example of making the invisible damage visible. Very much that DNA damage is invisible, and it only becomes visible when you've got, the manifestation in terms of skin cancers, etc. And so if you can make that invisible damage visible to the clinician, to the scientist, so you can do something about it, or you can actually make that information available to the patient so they can actually modify their lifestyle and say, actually, what I'm doing isn't good, therefore I need to change my lifestyle. And then you can show in another 12 weeks that actually that shift has actually benefited their skin, then they're more likely to continue to do that before any of those invisible damage becomes manifest later on down in life.
And what about then antioxidants? So when we think about antioxidants, these can be applied topically to the skin, or we can consume them orally, or people have them injected. What are antioxidants like in supporting the function of the mitochondria?
Yeah, so if you go back to that triangle of the vicious cycle where you've got all these exhaust fumes that are coming out from the factory, one way of mopping up those harmful free radicals, reactive oxygen species, is through antioxidants. And so generally the difference between free radicals and antioxidants are the fact that free radicals will take from you, as it were, if you're a molecule. They will rob you of your electrons, whereas antioxidants will donate, so create balance. And so we might know people in our social lives who are takers or givers. I don't know. I mean, one can...
I'm going to rename them a free radical, actually.
There might be free radicals in the room or antioxidants in the room. So antioxidants will actually mop up, or as it were, create balance within that whole oxidative stress cascade. And they do so with different mechanisms, different potencies. And what is interesting that we found is the fact that if you just do what's something called ORAC, ORAC, which is just a way of measuring the antioxidant potency of a molecule. So without any cells, just in the tube. you get a particular score. And if you kind of rank those, like, I don't know, I'm not into football, but let's say football, you know, your Liverpools and your...
Arsenal, by the way,
Yeah.
is right up there.
And your Man United and Tottenham, that should be doing well, but are at the bottom, right? And so you have that ranking. But what we and others have found out is that once you put those antioxidants into a cell, that whole league table gets messed up. So what looked really good, like an Arsenal, is at the top. Once it becomes in contact with a cell and the cell starts to metabolize it and everything else, the secondary metabolite or the tertiary metabolite, which is what you're really using as an antioxidant, doesn't work as well as it looked as though it did from the ORAC place, because the ORAC score was without any cells. But once you put it into the world of reality, where it's in a cell, then that antioxidant may not work as well as you thought it did. And instead of being an Arsenal, you end up being at the bottom of the table.
If you can hear some whining or some dog tag rustling, that's not Mark. It's my doggy. He just got up and left, actually, so he wasn't interested in the ORAC table. When we think about antioxidants, there's lots of different types of antioxidants. Do you want to give some examples that, in your expert opinion, you think are probably right up there as the ones that are going to be having most beneficial effect? And we're not going to hold you to this. This is expert opinion, level 5 evidence, you know. But what do you think?
So some of the well-known antioxidants that we're all familiar with are tried and tested. So vitamin C is clearly one. Often in combination with vitamin E, works really well. So nicotinamide or niacinamide works really well. We actually published a really nice paper looking at that in terms of mitochondrial performance. So those are often a lot of the key antioxidants. You've got other antioxidants which may or may not do well when they're compared with other things. So we've got a league table that we published quite a while ago, which involved dietary antioxidants as well. You know, you've got resveratrol, and resveratrol works really well, but it works not as a straight antioxidant because it works via another pathway. And it depends on what benefit you want from that. So in terms of when people say, what's the best one to use? My comeback is, it depends on what you want to see. If it's a straight antioxidant, then the vitamin C's, vitamin E's, etc., niacinamide, resveratrol. But what it does do is it helps the cell to recruit other helpers. So technically it's called an NRF2 keep 1 pathway, which is very detailed, but essentially it helps to recruit other things in the cell to help, right? It doesn't have a direct primary action. Whereas niacinamide, again, is often used as a primary, say, well, this is a great antioxidant. What that does is it actually enhances a process called mitophagy, which is essentially taking the bins out. It's essentially a recycling process in cells that takes out the damaged mitochondria. So niacinamide helps to recycle and get rid of damaged mitochondria by increasing mitophagy. So again, it's not working in that context as an antioxidant, it's actually having another function. So a lot of these so-called antioxidants have other functions as well, which people are finding out about. And so that's actually very exciting from a going forward point of view, because you think, hang on, these molecules are actually possibly better than we thought. But also, it's not a straight case of adding one with another, because what you don't want to do is have a treatment regime where it's all the same type of antioxidants. So you've got a straight antioxidant where, you know, you're seeking balance. You've got an antioxidant which actually might have properties where it increases your NRF2 keep 1 pathway, your recruiting pathway. It might be where this molecule actually enhances the taking out of bins, as it were, recycling damaged products in the cell. But also there's this aspect of chelation, where chelation means to sequester or trap away metal elements that give rise to free radicals. So what it does do is it kind of forms a little bubble around them and things like that. So it sequesters them away so they can't actually make all these harmful exhaust products that a factory would have. It's simple to start with, and I think of a little bit more complicated because a lot of these molecules have secondary functions, which actually could be synergistic to other things. So I would argue that rather than having a stack of the same type of molecule, you'd actually want to have molecules which will fire off all these pathways. You know, the secondary pathway, your straight antioxidant, your chelation, and you're taking out the bins. Now, if you had that, you would have a super duper product. You and I would develop it, Emma, and we'd become a very famous and rich.
What about coenzyme Q10?
Oh yeah, so coenzyme Q10, again, delivery is always a challenge with these things and everything else, but Q10 is a very lipid-soluble form, and Q10 will actually feed mitochondria, actually, because Q10 is very important for the way that the electrons are passed along the current, as it were. And so I came across Q10 before I came into the world of dermatology, because within mitochondrial myopathy patients, you would actually have some forms of Q10 or Q analogs to actually try and help to bridge the gap in a broken electrical chain. That's proven within mitochondrial treatments, actually. And there's other aspects one can give to patients with mitochondrial myopathy. And so within that, Q10 is obviously going to be important in boosting bioenergy within a cell.
So really the ultimate kind of thing is going to be combining these antioxidants. So it's got the antioxidant function, but it's also got these secondary functions that would all complement each other for that ultimate role of protection.
Yeah.
When we think about damage to the skin, so we have the mitochondrial DNA damage to the skin, and we have this process of aging occurring within our skin. But what I'm kind of starting to pick up a little bit is that with damage to the skin barrier, obviously inducing some inflammation as we age, and UV-induced damage in those senescent cells, and the mitochondrial stress and damage, do we see that if there is damage in the organ of the skin, that we're seeing it in distant organs? I've seen some in bones. I've seen a little bit related to kind of baseline inflammatory factors. But do you see something like this within the mitochondrial DNA? Is the mitochondrial DNA in the skin saying to somewhere else, the mitochondrial DNA, we're under attack here, you might be under attack too? Does that happen?
That is a very, very good question. One aspect is the fact that skin is a proxy for what's going on in other tissues. So essentially, it's almost the tip of the iceberg, isn't it? It's like you can see the skin because it's above the surface. And is the same thing happening in other tissues? And is the communication within that in terms of recruitment and everything else? It's a difficult one to answer. However, I mean, clearly within stress markers and stress proteins, when cells are stressed, stress proteins and heat shock proteins are released. So one might think that if that is then released in a system, whether it's bloodstream, lymphatic or whatever, therefore there might be recruiting or a communication from that point of view. Now, I don't know what proof there is in that in terms of what direct proof, but a lot of it would be incidental. What is interesting is the fact that within mitochondria, I think if you look at textbooks and people see them as individual organelles, well, they're actually a syncytium, in other words, a long sausage. So that's how mitochondria communicate with each other. And so actually you can get communication along mitochondria further than you would anticipate. Now, that clearly doesn't go from tissue to tissue, but within tissue, that's the case. If your body is undergoing a particular type of stress, and clearly UV doesn't penetrate deep down individual organs, but actually your individual organs will experience stress as in sleep. And, there are stress proteins that will affect our whole body. So clearly that stress load will affect your mitochondria in the same way of oxidative damage. Maybe not the UV direct damage, but certainly in terms of oxidative damage, you would expect to get that. Years ago, I used to work on prostate cancer, and actually we looked at mitochondrial DNA damage in the prostate gland. And because actually that's a highly oxidative gland, stress organ. And so the first thing that often was picked up was mitochondrial DNA damage rather than anything else, because that was an early marker of damage. And so actually mitochondrial DNA can be and has been used in other tissues as an early marker of damage, indicating what's going on in the bigger picture in terms of nucleogenes, because obviously nucleogenes are instrumental in cancer and everything else. And so what has been raised in the scientific world is, can mitochondrial DNA be used as an early biomarker, as a sentinel of changes that might occur in the nuclear DNA that would give rise to cancer?
Absolutely fascinating. And that's it for this episode of the After Hours Skin Clinic. We hope you've come away with a good understanding, including you, Ellie, of what mitochondrial DNA is and why it matters so much for your skin's health and longevity.
And a huge thank you to Professor Mark Birch-Machin for sharing his expertise. I always find it fascinating to hear straight from people that are at the forefront of research like this.
If you enjoyed today's episode, it would mean the world if you followed the podcast and left us a rating or a review. It really helps other listeners find us.
And we'd love to hear from you too. You can reach us on Instagram or by email. The details are in the show notes. So send us your questions and your thoughts and even ideas for future topics.
Thanks again for spending some time with us. Take care of yourself and your skin. Wear your SPF and protect your mitochondrial DNA.
And catch you next time here at the After Hours Skin Clinic.
As always, this podcast is for informational purposes only and is not a substitute for medical advice. Please consult your healthcare professional before making a change to your treatment.